So let's start looking at cycloalkanes in general, and then we are going to narrow down to talking about cyclohexane in particular. And so notice that we have a range in size, number of carbons of these cycloalkanes, and if you assume that they're flat, then their bond angles are quite different than what we would expect a tetrahedral carbon to be, except for cyclopentane, which is close. And so this is called angle strain, where the bond angle is different than the sp3 hybridized carbon bond angle should be, that 109.5 degrees. So what happens is cycloalkanes pucker. In other words, they're not flat, in order to relieve some of that angle strain and to get as close to 109.5 degrees as possible. And it turns out that cyclohexane can get to a tetrahedral shape. And so that's what's being shown here, down here at the bottom. This is called a chair conformation. And in the chair conformation, each of the bond angles for the carbons is 109.5 degrees. So the bond angle is what you would expect for a tetrahedral carbon. Meanwhile, we could look at it from the side using a Newman projection, which shows, again, that those bonds are just as far away from each other as possible. The Newman projection is a little weird because we're setting down two carbon-carbon bonds, the one over here and one over here. In other words, this bond here and this bond here. So imagine kind of putting that on its side. So if we look closer at the cyclohexane, you'll notice that there's two types of carbon-hydrogen bonds, and we call one axial, and those are going straight up and down. Okay. And so they're in red in this drawing on the left, and you can see they're axial because they're along, if you think about the ring axis, they're along that axis. Now there's also the blue hydrogens, and those are called equatorial. They're along the equator of the cyclohexane. And you can see, just looking at this pattern here, notice that the red axial is up, and then it's down, and then it's up, and then down, and then up, and then down. And we see the opposite pattern for the equatorial. Here's equatorial up, here's equatorial down, equatorial up, equatorial down, equatorial up, equatorial down. And then just a couple of other patterns to look for. Notice that every carbon has both an equatorial and an axial hydrogen, and that one of those is going to be up and the other one is going to be down. So one of the things that cyclohexane in particular can do is a ring flip when it's in that chair conformation. And so in a ring flip, let's look at it. Sometimes students think it's like a pancake flip, and it's not. Here's what happens. Notice again that we are at we have the blue, this time the blue hydrogens are axial and the red are equatorial. And slowly we get one side up, that's called a boat, that's actually pretty high in energy. And then the other carbon goes down. And now look what happens. All of the red axial hydrogens are now equatorial, and the equatorial hydrogens are now axial. The other thing to notice is that if it was if it was axial up, now it's equatorial going up. If it was axial down, or if it was axial down, like over here, then it is now equatorial down. And so the hydrogens can't jump to the other side of the ring. If it's down, it's going to stay down. But in a ring flip, everything that was axial becomes equatorial, and everything that was equatorial becomes axial. All right. So this is just another way of looking at that without all of the hydrogens. So you can kind of see the backbone of the cyclohexane a little bit better. Notice that if the carbon was down, it goes up, and if it goes up, it gets pushed down as we do, as we flip from one chair conformation to the other chair conformation. So it's not like you're putting a pancake turner or spatula underneath the chair and just flipping it over. It's actually that everything that was axial becomes equatorial and vice versa. You will want to probably do this with some sort of a model, or look online for the three-dimensional images of this, so that you can really see what's happening. So if you think about conformation, if you have a substituent on your cyclohexane, then in one conformation, it's going to be in the axial position, and then if you do a ring flip, it will be in the equatorial conformation. And so the question is, which one of these is more stable? And in general, the larger substituent or the single substituent will be equatorial to get it away from the two hydrogens that are 1, 2, 3 carbons, that if the substitution is at carbon 1, then that hydrogen at carbon 3 is going to have these diaxial interactions. And so this is kind of a steric interference. It can be avoided by having that methyl group on the equatorial position, or whatever the substituent is. So these are different by a ring flip, and the one on the right is the more stable conformation. So let's look at a similar question here. Applying that idea, the general rule is that the substituent will be equatorial. And so here you have an isopropyl group, and this is the axial position. This would ring flip to give you the equatorial position. It would be up, and that would be the more stable conformation, and that's conformation number 2. Number 3 you would probably get just by flipping the molecule over, right? And 1 you would get by turning it around. 4 is a completely different molecule, so that's not a conformation. And then here's another question. You might want to just pause the video for a second and see if you could answer this yourself. The question is, which of the following is the more stable conformation of trans 1-ethyl 3-isopropyl cyclohexane? And the first thing to realize is not all of these molecules are trans. Both 2 and 3 are cis. 3 is actually the most stable out of these conformations, out of these molecules, because both of the substituents are equatorial. But you're asked for a trans molecule, not a cis one. And so, so looking at the two choices that are trans, 1 and 4 are both trans. And in number 4, the larger substituent, the isopropyl group, is equatorial. And so this one would be more stable.